Welcome to lecture number 4 of the course on high performance computing. Let me remind you quickly what happened in the previous few lectures. We have been looking at the basic organization of a computer. You'll remember that there are 3 main parts to a computer: the CPU, the main memory, and the I/O devices. We looked in the previous lecture a little bit at the CPU, understanding that there are many registers in which data can be stored temporarily while it is in use by the processor. We also looked at the main memory a little bit. We understand that main memory is capable of storing the entire program in execution, including both its instructions and its data. And in looking at main memory, we realized that it is slower than the processor, and therefore that's why the registers the general purpose registers are important. It is possible for the program to cause data to be copied from main memory into a register, and therefore accessible by the processor at much higher speeds than if it had been in main memory. And as far as main memory is concerned, the key points we made last time are that it holds both instructions and data, and that individual elements in memory are referred to using addresses, which are integers, unique integers associated with the different entities in memory. An important concept in connection with addressing is what is called byte ordering. We understood that there are typically 2 alternatives that are used: little endian and big endian byte ordering, and this is of course an important consideration. Today we'll continue to look at main memory with one final consideration, and that is what is known as, other than byte ordering, the next important consideration is what is known as the word size or word alignment. Now, in hearing about computers, we often hear people talk about a 32-bit computer or a 64-bit computer. And we understand that both 32 bits and 64 bits are referring to the size of something. And more specifically now, we'll understand that it's actually referring to something known as the word size. So the word size of a computer gives us an idea about what the typical size of an integer, or let's say a pointer, would be on that computer. And therefore, if you're told that you have a 32-bit computer, we would understand this means that the typical integers on that computer are stored in a 32-bit unit. And similarly, the size of a pointer, like a pointer to a structure or a pointer to an integer, would also be of the same size. So today we hear about 32-bit, which means 4-byte machines. We also hear about 64-bit machines. And the thing to note here is that, as we learned in the case of byte ordering, if there is an element in memory which is more than 1 byte in size, such as in this diagram that we have on the screen, the 4-byte entity 1A, C8, B2, 46, whatever it may be, then there is the possibility that it is a word. In other words, in my C program, it might represent an integer variable, let us say. And the concept of word alignment then becomes important. Now, the concept of word alignment is quite simple. Sometimes when you are compiling a program, you may get a warning which says your integer variable x is not word aligned, and may have wondered what this means. You notice that I mentioned that this is a warning that you may get. It may not be an error, meaning that it's not a mistake in your program, but it's just something that you may want to change to get your program to run more effectively. Now, the idea of an integer variable not being word aligned is that its address, its starting address, may not be what we call a word boundary. Now, if we look at the entity which has been darkened in the diagram above, you'll notice that it is 4 bytes in size, which is 32 bits in size, and it seems to start at the address 400, going on until the address 403. The key thing to note is that it starts at the address 400, and therefore the next entity in memory would start at the address 404. If you actually look back to the beginning of the first bytes in memory, byte 0, 1, 2, 3, etc., the concept to have in mind here is that if I had put word-sized entities into each of the units of memory starting from byte 0 onwards, then the first word-sized entity would have started at address 0, the second word-sized entity would have started at address 4, and so on. And I would then say that these elements in memory are word aligned, in that the starting address of that 4-byte entity, or the word-sized entity, is itself a multiple of 4, from the perspective of having started from the beginning of memory and put only word-sized entities into memory. So in that sense, the word boundaries among memory addresses would be 0, 4, 8, 12, etc., all the multiples of 4. And that's where the word alignment concept comes in. You would say that an address is word aligned on a machine which has a word size of 4 bytes if the address, the byte address, is a multiple of 4. And this could have some performance connotations. It won't have any impact on the correctness of your program. It's not necessary that all your variables be word aligned for the correct execution of your program, but it may be important for the efficient, fast execution of your program. So I just wanted to make sure that we understood the concept of word alignment. Now with this, we have a starting idea about the various components of the computer system, the processor, the memory, and we can now go ahead and so with this we have the good understanding of the essential properties of the processor or CPU and the main memory, and we'll now take one step back and try to understand the computer system from the perspective of the instructions that the computer system is capable of executing. And technically this is referred to as the instruction set architecture of the computer, often abbreviated as ISA. So in short, the instruction set architecture of a computer is the view of the computer from the perspective of a programmer, or to be more precise, a compiler. Why do I say to be more precise? If you think about it, most programmers who use computers do not actually know the instructions, the low-level instructions of the computer, since they program in a high-level language such as Java or C or C++ or whatever it may be. And therefore, to say that the instruction set is the view of the computer to the programmer would be misleading. Most programmers do not view the computer in this way. But when I write a C program, the C program gets compiled, it gets converted into instructions of the kind that are understandable to the hardware, and therefore the compiler itself must have a view of the computer which understands instructions. Hence the second description, which says that the ISA is the view of the computer from the perspective of the compiler. But again, there are programmers who do program at this level, and therefore for those programmers this would be their perspective of the computer. Now typically for any computer processor or computer, particularly specifically for the processor, one will find the instruction set architecture completely described in a manual that is available from either the manufacturer of the processor or from the website, other websites. And this book would typically be called the ISA manual, or the instruction set architecture manual. And typically it's a very large book because it contains information about each of the instructions in various ways, which is all the information which might be needed by a person who's going to write a compiler, or by a programmer who wanted to use those instructions. So in general, there are two kinds of computers from the perspective of the styles in which instruction sets could be designed, and they are referred to as the CISC and the RISC styles of design. Now we're going to look at a particular example which is of the RISC style, but for completeness let me just tell you that the CISC style, which is the complex instruction set computer style, as opposed to the RISC style, which is the reduced instruction set style. In the CISC style, you could have individual instructions which are somewhat complicated, hence the name complex instruction. So in the individual instructions may actually do multiple operations, whereas in the reduced instruction set style of designing computers, the instruction set would be made up of individual instructions, each of which does only one somewhat simple operation. And you might imagine that RISC computers being simple and having simple instructions may result in hardware that can do those simple instructions very fast, whereas the CISC computers having more complicated instructions, the hardware is obviously going to be a little bit more complicated as far as the individual instructions are concerned. And also from the perspective of the compiler designer, it may be easier to generate simple instructions, to translate a C program into simple instructions. For these and other reasons, a large number of the current processors use the RISC style, which is why we are going to concentrate on the RISC style. Now to get a specific idea about the instruction set of a RISC style computer, we do need to look at an instruction set. So let me first of all tell you what you should expect to see if you opened an instruction set architecture manual. I'm not suggesting that anyone do this because, as I said, it's a very large and very detailed book. But it would be useful for us to understand instructions at this level. So I mentioned that instruction set architecture describes the machine from the perspective of the programmer or the compiler. And you may, for example, have heard of the Intel x86 architecture. Many of the computers, the laptops, desktops that you use actually implement the Intel x86 instruction set. So every instruction set has a name, and one can get the manual based on knowing the name of the instruction set. What the manual will contain is a complete specification including 3 key components. The first key component is a description of what the different kinds of instructions provided by the instruction set are. And typically the instruction set architecture manual will contain 1 page for each of the instructions. So if there are 200 different kinds of instructions, there would be 1 page per instruction, meaning 200 pages just for that purpose. So the first important component of the ISA manual would be the description of the individual instructions. The second component is a specific description of how the operands to the instructions are to be specified. And the term for how operands are specified, technical term that is used for this, is to refer to them as the addressing modes. So we will try to understand a little bit about what the different kinds of commonly used addressing modes are in this lecture. Finally, the third important component of the ISA manual is going to be a specification of what each instruction looks like in the binary form. In other words, what bit pattern would correspond to each of the instructions, and this is referred to as the instruction format. And once again, this would be clearly of great importance to the compiler writer, who has to write a program which can translate a C program, which you or I could read, into a binary bit level machine language program which can be executed by a computer. And obviously the format of the individual instructions in bits would be necessary to do this. Okay, first let's start off by trying to understand a little bit more about what the different kinds of instructions might be included in an instruction set architecture. Now, very clearly, the designer of an instruction set architecture would have to include all of the different instructions which might be necessary for the typical kinds of programmers, the typical kinds of programs that are written by users of the computer system. And therefore, depending on what application the computer system is likely to be used for, the instruction set architecture could differ. We will make some comments in this lecture about the instruction sets of general purpose processors, which are meant for generic kinds of uses, not for specific uses. A specific use might be something like a processor which is designed to be used inside a cell phone. That might be a little bit different from a processor which is used to be inside a personal computer. A personal computer must have general capabilities. The processor inside a cell phone could have more specific capabilities and therefore might have a more finely tuned instruction set. But as far as we are concerned, for the kinds of computers which we work on, we'd expect that there must be a good representation of arithmetic and logical instructions. In other words, instructions which can do arithmetic operations such as add, subtract, multiply, divide, both on integers and on real values. In addition, we might expect that there should be instructions which can do logical operations. We'll see a little bit about what logical operations are. So the arithmetic instructions we are quite comfortable with, add, subtract, multiply and divide, but I'll also include one more in this, and that is an instruction which can do comparison to see if one integer value is less than, greater than or equal to another integer value, for example. You might argue that this could be done using the subtract instruction, but the danger of using the subtract instruction is that when I subtract one integer from another, there is the possibility of an overflow. In other words, let's suppose that I have a very large negative value and I subtract from it a very large positive value, then the result is going to be an even larger negative value which might not fit in the bits available as per the number of bits available for representing negative signed integers. Therefore, rather than using subtract to compare two integer values, it's better to have a special instruction which might be able to do the comparison, through which one can do the comparison without doing a subtraction, since a subtraction might result in an error condition. The other thing I'd like to again point out is that as far as arithmetic constructions are concerned, there may be a need to provide separate instructions for the different kinds of arithmetic that have to be done. Right? Integer arithmetic is different from real arithmetic, which is represented in computers typically by floating point arithmetic. There would be separate hardware to do these two, and therefore there must be separate instructions for the purpose. So there could be two sets of arithmetic instructions. For example, there could be an add instruction for integers and a separate add instruction for floating point values. Okay. Next, as I said, there would be a need for logical instructions. The logical operations are OR. Examples of logical operations are OR, AND, NOT, and exclusive OR. And those of you who are familiar with these will realize that they are operations at the bit level. Right? So the OR operation between two bits and so on. So almost all instruction sets provide these logical operations. So with this, you understand that most of the expressions inside the programs that you write could get evaluated using the instructions provided in the arithmetic and logical instruction set. In addition, it often happens that some other instructions are useful, and that most instruction sets will contain instructions called shifts and rotates. A shift instruction is an instruction which will take a value which might be stored in a register and cause the contents of the register to get shifted either to the left or to the right. In other words, the bit pattern in the register, the least significant bits in the register will move to the most significant part of the register, thereby increasing or thereby changing the value in the register. So there are different kinds of shifts which might be implemented, some of which might have meaning as arithmetic operations. And with some thought, you will realize that shifting a binary value, an integer value, for example, to the left by 1 bit may be equivalent to multiplying it by 2. And therefore, there may be this notion of using shifts to implement some kind of arithmetic, multiplication, division, and so on. There are also instructions which are called rotate, in which the bits, after being shifted, which would otherwise fall off the most significant end, could be rotated back to the least significant end. So instructions of this kind, which might actually be used to do arithmetic, but which may otherwise be used for the simple purposes of shifting data to the left or to the right, or rotating data within a register. So this is a typical complement of arithmetic and logical instructions. Now, another class of instructions, which is clearly necessary for the kinds of processes that we are talking about, are instructions which can be used to transfer data from one place to another. Now, we know that the data which your program deals with is going to start off, when your program starts executing, with the data all being present in main memory. But that occasionally, in order to improve the execution time of your program, you may want to transfer some of the data, for example, the variable x, the value associated with the variable x. You may want to transfer it from main memory into a register to make the access to that value even faster. So there must be instructions for this kind of a data transfer to take place. So we'll talk about 2 or 3 different kinds of data transfer. The first is what is typically known as a load, an instruction which can be used to copy data from main memory into a register. So one can talk about loading the variable x from memory into register R1. There must be also the converse data transfer, where one could copy a data value from a register into main memory, and that is typically referred to as a store. So there could be store instructions in an instruction set to copy data from a register into a main memory location. And finally, there could be instructions which are generically known as move, which could be used, for example, to copy data from one register to another register, or from one memory location to another memory location. And some instruction sets may contain move instructions. So move is a more generic term. Load will typically refer to an instruction that can be used to copy data from main memory into a register. And similarly, store will typically refer to an instruction that can be used to copy data from a register in the CPU into main memory. So clearly, it would be in any processor which has registers, general purpose registers, it would be necessary to have instructions of these kinds, and these instructions are referred to as data transfer instructions. So that's 2 classes of instructions we expect to find in our general purpose instruction sets. Now, a third, if you think about it a little bit, would definitely have to be control transfer instructions. There will be situations in a program where I am not happy with the sequential execution of first executing the first instruction, then executing the second instruction, then executing the third instruction, and so on. Unless I have some kind of instructions which can be used, for example, to create a loop or to create an if-then-else, my programs will be quite uninteresting, and it would not even be possible to easily compile C programs which contain constructs like loops, repeat loops, while loops, or if-then-else into machine instructions. So the control transfer instructions are primarily there to allow control to change from the default pattern of executing instructions in order, first, then the second, then the third within the program, to more interesting kinds of execution patterns based on the high-level constructs that I just referred to, if-then-elses, repeat, while, etc. So what kind of control transfer instructions could one find in instruction sets? The answer is there are several kinds that one finds, and they typically go by names such as jump, conditional branch, function call. If you think about the event of a function call, you realize that that too is a control transfer, and return. In other words, the return from a function call to the point in the program where it was called. So most often when one refers to a jump, one is referring to a control transfer instruction which is not conditional, which is why the term conditional branch or just branch, so the conditional branch is often referred to just as branch, is meant for uses where a condition will be specified within the instruction. If the condition is true, then the control transfer will take place, whereas if the condition is false, the control transfer will not take place, and instead of transferring control to that specified instruction, the next instruction in the program will simply be executed. So your typical instruction set will have a variety of different kinds of instructions for different purposes. We realize that the jump might be very useful to implement something like a go-to. The conditional branch would be very useful for if-then else's, for repeat loops, for while loops, etc. conceivably. The function call would be essential for the implementation of function calls, and the return from a function call to the point of call. Now, there are other instructions that one can expect to find in an instruction set, and I'll sort of generically classify them as other instructions. The functionality that we are used to using in programs actually typically falls or can be satisfied by the first three classes of instructions. But there are other things which must be included in an instruction set for reasons that might not be obvious at this point. But let me just give you one example. There may be a need for an instruction that can be executed for the graceful shutting down of a computer. Here I'm not referring to an instruction that's going to be used for the end of the execution of a program. That's a much simpler event. Here I'm specifically referring to an instruction that may have to be executed for the powering down of the computer. That instruction might be called a halt instruction, and that's very clearly a very special kind of an instruction, which a typical user is not going to use in a program. If I'm writing a program, it's very unlikely that I will have to use the halt instruction, since it's unlikely that I'll have to shut down the computer as part of the execution of my program. Whereas some more important programs which handle the management of the computer as a whole may well have to use instructions of this kind. And there could be several other instructions of this kind which are not meant for the usual programmer, but are meant for the privileged programs, the very special programs that control the computer system as a whole. So there are many different kinds of instructions, and they are typically classified into these four classes. Please do bear in mind that in the arithmetic and logical instructions there could be subclasses, such as the arithmetic instructions which are of integer type, the arithmetic instructions which are of floating point type. Okay. Now, with this we have an understanding of the first important part of an instruction set architecture description. Let's move to the second. I had indicated that the second important part, there are three components one finds in instruction set architecture manual or description. The first is the complete specification of all the instructions. The second is the addressing modes. So let's look at addressing modes next. So here in the slide we talk about the operand addressing modes, and the question that one should first ask is, where can the different operands to an instruction come from? So I have an add instruction. What are the different possibilities as far as where its instruction operands could come from? With a little bit of thought, you'll realize that any add instruction is going to have two kinds of operands. It's going to have its source operands, which are the input values to the instruction. The word for the input values to the instruction, the technical term is to refer to them as the source operands. And then there's going to be another operand, which is the place or the destination of the result of the add, and that would be referred to as a destination operand. So your typical add instruction may have two source operands and one destination operand. And the question of how the operands are specified is what is taken into account or indicated by the instruction set architecture's addressing modes. Now, where could the source operands be? If you think about it a little bit, you'll realize that the source operands to an instruction could either be in memory, or they could be in registers. Therefore, we're going to have different addressing modes for operands which are in memory, and separate addressing modes for operands which are in registers. So there are going to be different kinds of addressing modes, which is why we're going to treat the topic of addressing modes as much more detail than we looked at the topic of instruction set instructions, because it's more important. It's really critical for us to understand what the different kinds of addressing modes are. It's a much more subtle point. As far as the different kinds of instructions were concerned, for us people who have programmed before, it was fairly obvious that there had to be arithmetic, logical, etc. The different kinds of instructions. Whereas this whole concept of addressing modes may appear to be quite new to many of us. Okay, so let's start by trying to understand some of the addressing modes which are used for operands to instructions where the operands are within a register. Now, the simplest possible case is where the operand value is contained within one of the general purpose registers of the CPU. And in this case, the addressing mode is referred to as the register direct addressing mode, suggesting that the operand value is directly available within one of the general purpose registers of the CPU, and that therefore within the instruction one will expect to find the identity of that register and nothing else is needed. Right? So in short, in the case of the register direct addressing mode, the operand value is within the specified general purpose register. Let's look at an example of an instruction which uses the register direct addressing mode. Now, for this and the subsequent examples that I'm going to use in today's lecture, and in fact for the lectures to come, I'm going to assume that the general purpose registers of the computer that we're talking about are referred to or numbered as R0, R1, R2, etc. Now, within the binary form of the instruction, they may not be represented with the R. Just the 0, the 1 and the 2 will suffice. But since we are human beings and we would like to be more comfortable with the notation that we use, at least in a lecture, I'll use R0 to represent the general purpose register R0, etc. So let's look at this instruction. Over here I've shown you the instruction on the left, and on the right is a comment. Okay, so here we have an add instruction, add R1, R2, R3, and the way you should interpret this instruction as this is an instruction which does an addition. More specifically, its source operands are R2 and R3, and its destination operand is R1. So that's the convention that we are going to use in the lectures to follow. I'll put the destination operand first and the source operand subsequent to that. So what is this instruction actually telling me? It's telling me that there are two source operands to the add instruction. The first source operand value is contained within general purpose register R2. The second source operand value is contained within general purpose register R3 of the CPU. So these two values will have to be taken. They will have to be added by the ALU. And after this, the result should go into general purpose register R1 of the CPU. And in this case, all the three operands are actually specified in this register direct addressing mode. So just to make sure we understand this, the two source operands are R2 and R3. The destination operand is R1. Let's suppose I had a situation where before this instruction executed, if I had looked into the registers, I found that register R1 contained the value 17, register R2 contained the value 24, and register R3 contained the value 37. Then what this instruction is asking is that the value within R2, in other words 24, is added to the value within R3, in other words 37. The sum of 24 and 37 is 61. So after the addition has been done, this instruction is requesting that the value 61 go into register R1, and therefore the effect of this instruction would be that R1 will have a new value of 61. And that's all there is to understand about the register direct addressing mode. It is the way that an instruction can specify an operand which is currently available within one of the general purpose registers. Very clearly, the program would have had to load the value from its main memory location into that register by some previous instruction. So register direct is the simplest addressing mode. Right, so what information must be present within the instruction for an operand which is specified in register direct addressing mode? Very clearly, the identity, other than the operation which the instruction is meant to do, such as the fact that this particular instruction is meant to do the add operation, the identities of its source and destination registers. Therefore, in this case, the two source registers are R2 and R3. The destination register is R1. Therefore, the identities of R2, R3, and R1 would have to be present within the instruction in the case of the register direct addressing mode. Now that was nice and simple. Let's look at a slightly more complicated addressing mode which deals with operands which are in registers. Now, in fact, I can think of only one more which is generally likely to be available, and that is the immediate addressing mode. Now, the idea of the immediate addressing mode, as the name sort of suggests, is that the operand value is included within the instruction itself. It is actually not present in any of the operand value is not present in one of the general purpose registers of the processor, but rather it is present within the instruction itself. And I'll come back to that, why I have included the immediate addressing mode in this particular slide a little bit later. Let's look at an example. So here I have an instruction, add R1, R2 followed by the number 7. And the interpretation, the meaning, which I provided in this comment, is that the value within R2 is to be added to the value 7, and the result of the addition is to go into register R1. So one of the operands to the add instruction in this case is the value 7. And if you look at the instruction, you see the value of the operand present within the instruction in what is known as the immediate addressing mode. And just to run through this example, very clearly, if R2 contained the value 24 prior to this instruction, after 24 and 7 have been added, the result is 31. 31 would be the new value of R1. Now, what information must be present in the instruction? Very clearly, the immediate value 7 must be present within the instruction. That's the meaning of an instruction of this kind. Now you may be wondering, why did he include immediate addressing mode on a slide entitled Addressing Modes Operand in Register? The operand 7 is not in a general purpose register. So you may be wondering why I included this addressing mode on this slide. If you think about it a little bit, you realize that when this instruction is being executed, the instruction as a whole is present within the CPU. And in fact, it is present in one of the special purpose registers of the CPU known as the instruction register. It's only if an instruction is present within the CPU, specifically inside the instruction register, that it can be executed. The instruction has to be fetched from main memory into the instruction register in order to be executed. Therefore, when this instruction is executed, it is present inside the instruction register, and therefore the value 7 is also present inside the instruction register within the CPU, which is why I have included it in this slide. It is a situation where the operand value is present in a register. It just happens to be the instruction register. Okay, so these are typically the two kinds of addressing modes relating to operands being present within registers. The first case, the case where the operand is present in a named general purpose register. The second, the immediate addressing mode, where the operand is present within the instruction register, having been specified within the instruction. Now, the bulk of the addressing modes, which we are going to study from this point on, relate to operands which are not present within the CPU. They are not present in any register, but rather the operands are present in main memory. And there are many different mechanisms, in other words, many different addressing modes, which could be used to specify operands, the location of an operand in main memory. Now, the first which I will talk about is something known as the register indirect addressing mode. Remember that the previous slide, I will go back to the previous slide, the addressing mode which we had there was called the register direct addressing mode. So, this is a different name, the register indirect addressing mode. The idea of the register indirect addressing mode is that the operand is present somewhere in memory, and specifically the memory address of the operand is specified within a general purpose register. That is why it is known as register indirect. One of the general purpose registers will indirectly tell you the operand value, because that general purpose register will contain the address in memory of that operand value. Let us look at some examples of this. One example should suffice. So, here again I use an add instruction. This add instruction is adding to R1 an operand from memory which is specified in register indirect addressing mode. So, the register indirect addressing operand in this case is shown with R2 within brackets. That is an often used convention in instruction set notation in many assembly languages. When they show a general purpose register and put parentheses around it, that is an indication that they are talking about an operand which is specified in register indirect addressing mode, whereas operands which are specified in register direct addressing mode may just be represented by the identity of the register. So, this particular instruction actually has one destination operand and two source operands. One of the source operands is specified in register direct addressing mode. The other source operand is specified in register indirect addressing mode. So, the first source operand is coming out of register R1, the value is present in register R1. The second source operand value is coming out of memory. Where in memory? That is what the register indirect addressing mode tells the processor. So, to get an example of this, we need a more thorough picture. We have to know the current contents of register R1, the current contents of register R2, but we will also have to know the current contents of various memory locations, which is why for this particular example I show you some memory locations in terms of the different addresses and some of the values relevant for this particular example. So, let us suppose that I have this instruction and I have a situation where R2 currently contains the value 32, I am sorry, R1 currently contains the value 32, R2 currently contains the value 100. So, what then is the meaning of this? The first operand value is 32. The second operand is contained within the memory location specified by register R2. In other words, it is contained within memory location 100, which means that the second operand value is 10. So, that the result of the addition is going to be to add 32 to 10 yielding 42, which will be the new value within register R1. So, the register indirect addressing mode is a simple example of an addressing mode used to specify the location in memory of an operand. In this case, the operand value was 10 and it was specified in register indirect addressing mode by indicating that register R2 contains the address of the operand. Okay, so what information must be present within the instruction if an operand is specified in register indirect addressing mode? Simply the identity of the register which contains the operand address, in this case R2. And that is why we saw in the example the identity of R2 had to be specified within the instruction for an operand specified in register indirect addressing mode in this way. Okay, moving right along, we could have more complicated addressing modes. Let me show you an example, a minor extension to register indirect which adds to its functionality substantially. Now this addressing mode, which I'm going to talk about next, is often referred to as the base displacement addressing mode. As I said, it's a minor extension on the register indirect addressing mode. Now what happens in the case of base displacement addressing mode is that the memory address of the operand has to be calculated, and it is calculated as the sum of the value in the specified register along with a specified displacement. Recall that in the case of the register indirect addressing mode, the memory address of the operand was the value in the specified register. We didn't have the additional computation of a sum with a specified displacement. That's why I said this is an extension of the register indirect addressing mode. Moving right along, let's look at an example. So again, an add instruction, add R1, R1. R1 is the destination, it's specified in register direct. R1 is the first source, it is also specified in register direct addressing mode. Here we have a new notation, and this is a notation which again is often used to specify an operand in base displacement addressing mode. So here what is being indicated is that the value which is contained within register R2 is to be added to the specified displacement, or the value 4, and what the result of doing that addition will give you the memory address of the operand to our add instruction. This sounds complicated, but as we're going to see in later lectures, this is a very useful kind of an addressing mode to have. Let's just look at an example again. We'll use the same example from the previous register and memory picture. So once again, R1 contains 32, R2 contains 100, and memory is as shown. So when this instruction comes up for execution, in order to find out what the second operand is, what the processor has to do is, it has to look at the contents of R2, where it finds 100. Then it has to add to that value, the value 4, yielding 104. It then knows that the operand to the add instruction is contained at memory address 104, and that the value of the operand is in fact 35. The first source operand was previously identified as being 32. Therefore, this add instruction is going to add 32 to 35, yielding 67, which will be the new resulting value in register R1. So this sounds like a lot of work to do just to specify where an operand is in memory, but I'll just make two observations. The first is that, as I said, this is a simple extension to the register indirect addressing mode, and in fact whenever you see a base displacement operand, you should bear in mind that if a displacement of 0 was used, then when the address of the operand is calculated by the processor, it will amount to being exactly the same as the register indirect addressing mode, which is why a processor which gives you the base displacement addressing mode might not actually give you the register indirect addressing mode. It's not necessary. You can achieve the register indirect addressing mode yourself by using a displacement of 0. So it is not the case that every processor that you see will have all the addressing modes that we're going to talk about. It is very clearly not necessary to have the register indirect addressing mode at all if the base displacement addressing mode is present, which might explain why the base displacement addressing mode is important. It is a generalization of the register indirect addressing mode through which more functionality is available and allows the register indirect addressing mode to also be achieved. And when we look at some examples in coming lectures, you realize that it is very useful for the kinds of situations that come up when the kinds of programs that we write, C programs or Java programs, execute. So what information must be present in the instruction as far as an operand specified in base displacement addressing mode is concerned? Very clearly, two pieces of information. The first is the identity of the base register, in other words, the fact that the base register of this operand is R2, and secondly, the value of the displacement, which in this case was 4, the value which is to be added to the contents of the base register in order to compute the address of the operand in memory. Right? And again, I'll repeat that this is one of the key addressing modes that we are likely to encounter. Okay, now moving right ahead, I'd like to talk a little bit about the next addressing mode, which is called the absolute addressing mode. Now, the absolute addressing mode is a simple addressing mode in that the memory address of the operand is specified directly within the instruction. And therefore, to look at an example of this would be simple. We would see something like, again, I'm just using the add instruction generically. and there's an operand here in a new format. This is not the kind of format that we used for any of the previous addressing modes. I'm just using it for the absolute addressing mode. This is not a very standard notation for the absolute addressing mode. Every instruction set, every assembly language will tend to use its own notation. So in our examples, I will use this count sign in front of a value to indicate that it's the absolute addressing mode. So from the description, we understand that this means that the operand is available at memory address 100, and that therefore the address 100 in memory is where the operand value will be available. That will be added to the contents of register R2 to provide the value that is to be put into the destination register R1. Now, let me just back off a little bit and point out that there are other instructions other than arithmetic and logical instructions within an instruction set. For example, there are data transfer instructions and there are control transfer instructions. And it might be the case that for something like a control transfer instruction, for example, for a jump, it might make a lot of sense to use this absolute addressing mode. And again, the way to think about this might be, I asked you to relate the jump instruction to, let's say, a goto in your C program. So what form did the goto take in your C program? How did you specify the destination, the target of the goto within the C statement? You actually had a label. So you are indicating that the current instruction should cause control to transfer to the instruction which is labeled L. And it is likely that the jump instruction, if it is going to relate to the goto statement of C programs, is going to have the capability of specifying an arbitrary instruction in the program, for which reason the absolute addressing mode might be the most useful addressing mode to use for the jump instruction. Whereas it might not actually make a whole lot of sense to use the absolute addressing mode in the way that we have shown in this example. The only reason that I have used the absolute addressing mode using the add instruction example is because I have used the add instruction example for all of the previous instruction addressing mode descriptions. So do bear in mind that there are other instructions other than the add instruction. There are various instructions for which different addressing modes might end up being useful. Just to carry this example a little bit forward, let me point out that one of the other control transfer instructions that we had was the conditional or branch instruction. And I had indicated that the conditional branch instruction might relate to, in an if program, the if then else. Recall that in the if then else construct in a C program, you have a condition, and if the condition is true, then the then part of the if then else is executed, but if the condition is false, then the else part of the if then else is executed. And you may have C programs in which you have if then elses. So clearly there's going to be an instruction which could be used to check whether a condition is true, and if the condition is true, transfer control to the then part, and if the condition is false, transfer control to the else part. Now the property of the if then else is going to be that typically the then part may be very close to the instruction which evaluates the condition, the conditional branch instruction. And therefore, it may be unnecessary to have an arbitrary memory address associated with the conditional branch instruction, but rather we may want to have some kind of a abbreviated version of the memory address present inside the the conditional branch instruction, for which reason we might find other addressing modes which make sense for the conditional branch instruction. And I'll refer to this in the next lecture when we continue our discussion of the different addressing modes. But in brief, we've talked about several addressing modes up to this point in time. Some of the addressing modes make sense for any instruction set. For example, I have suggested that the register direct addressing mode from the previous slide is likely to be present in any instruction set for a processor which has general purpose registers. The immediate addressing mode is also likely to be present in any such processor. The same is likely to be true for the base displacement addressing mode, but not necessarily for the register indirect addressing mode, since there will be situations where you don't expect the processor to provide something that can be implemented using one of the other addressing modes. The absolute addressing mode is likely to be present for some instructions. It may not be present for add instructions, since it might be difficult to imagine situations where a programmer would prefer having an operand in memory to having the same operand in a register. Having the operand in a register will allow the instruction to execute so much faster. Therefore, one would not expect to see all combinations of all addressing modes with all instruction types in an instruction set. The person designing the instruction set will judiciously have for each different kind of instruction based on its type, arithmetic, logical, control transfer, data transfer, maybe one or the other of the different addressing modes, rather than having all the addressing modes available for all the instructions. By doing this, the complexity of the instruction set can be reduced, and the complexity of therefore the complexity of the hardware which is used to implement the instruction set can also be reduced. So with this, in this lecture, we have seen that the instruction set architecture of a computer involves three different components: the complete description of the instructions, the different kinds of instructions which comprise the instruction set, a complete description of all the addressing modes which are used for specifying operands within the different instructions of the instruction set, as well as the format of the instructions. In the next lecture, we will continue our discussion of the different addressing modes, and then we'll proceed to look a little bit at the formats before proceeding to look at several examples of, we'll look at a specific example, a complete instruction set in some detail, and then look at different code examples which are implemented using that instruction set. Ultimately, the best way to understand an instruction set is not by reading the instruction set architecture manual, but by using the instruction set. And we will therefore look at some specific examples of code fragments. We will look at them in the instruction form, not in the binary form, but in the assembly language form. So with this, we will stop lecture 4 and continue with addressing modes in lecture 5. Thank you.